from closest to the Earth and work our way out. So the first group is the comets group. Esty, get on.
Oh.
What? There, yes. I keep forgetting.
Sorry.
Eskin Jared and recently.
Sorry, can you just give me a second? We're getting feedback because I did hold on.
And we're getting feedback. Just a moment.
Okay, could you try talking?
So I can try talking. Yes, we're having a little.
No, we're not having any trouble. It's all good.
Interesting.
We're all good.
Yes.
Damn it! Sorry. Okay. How do the presentations go? No.
Okay, which computer is controlling? The controlling from this one. Okay, so I will try. So Lisa and Eskin have been working on comments. Eskin's a returning student that has worked on mostly asteroids, but also some exoplanets. Risa has been she has been the comet girl. She's absolutely loving comets. So I will let them give their presentation on comets. Great being.
I'm Eskin Duran.
And I'm Rita May Basig, and this is our project, Comets Breaking the Ice. First off, what are comets and why they're interesting to study? Comets are solid bodies made out of ice and dust. They outgas, or it's the ice to gas transformation, which causes gas and dust tails. Since they have the two dust tails, we will be focusing on mainly on the dust tail. Here we have an image of a comet that has a perihelion, or closest to the sun, and its orbit is on the outer edges of the solar system, and aphelion is the farthest from the sun. What is our goal for this project, and what do we hope to do? Our goal for this project is to predict and construct the light curves of our comets from different observations. And we will do this by predicting the magnitude of our comets as they reach the different points in their orbits. Here we have an example of a light curve from its brightness to orbit, and the data points show where the orbits are.
So what is our motivation behind studying and choosing these comets? And this is basically because these comets are what is known as a long period comet. That means they come from kind of the outer edges of our solar system from a body called the Oort cloud, which basically and by studying these comets, we can basically just get a better idea of like the early formation of our solar system and like help us to better understand our solar system altogether. Specifically, our two comets, C2019 U5 and C2019 U4, T4. We chose these comets mainly because they were very active. They had very big tails. And in the case of U5 specifically, it had an unbound aphelion. That means basically that the farthest point in its orbit away from the sun was just undefined. That means it's like relatively new. And I thought that was a really cool reason that was one of the reasons why I wanted to study this comet. And for T4, it has a really close perihelion. That means I think next week, actually, it will reach its closest approach to the sun, which is pretty interesting to be able to have observations this close to the perihelion.
Okay. As Ken has mentioned, we are looking at long period comets. We have the two comets, C2019 U5 and C2019 T4. On the bottom, we have the orbital properties, and TP is our perihelion dates. And the images are just examples of what a comet looks like.
So specifically on C2019 U5, this image up here up top is actually a picture that I recreated of this comet, and I did this the telescope basically takes the pictures in black and white, and by combining and stacking different filters, I was able to create a color image of our comet. And then these bottom two images kind of give like a representation of our comet's orbit. This image here on the right shows the circular orbits that are more colorful are the orbits of the different planets in our solar system. And this more black and white one is the orbit of our comet. And I thought it was cool to show how this comet specifically passes through kind of the plane of our solar system. And then this other image over here, this gives like another representation of my comet as it approaches, reaches, and passes its perihelion, or closest approach to the sun. This is another way of representing the light curve of my comet, and this was using amateur astronomer data from the Minor Planet Center. And this just basically shows kind of like the process of the comet being not so active down in these lower regions, not emitting that much brightness from its tail, and then slowly getting more and more active. And then this red line is just a prediction of what the brightness levels might reach.
Here we have the comet C2019 P4. This is also a representation of what its orbit is. And this is taken from the JPL horizon. Here we have our comet in RGB filters. This is just another way of able to see the comet and its tails, and how you can tell the different brightness in each filter and its dust grains. Here we also have a light curve from C2019 T4, and as Ken has already described the light curve, we have the data points that were gathered from the Minor Planet Center.
So for this project, we used a variety of resources, including the Las Cumbres Observatory, which we used for some of our data collection, and then we used also the CADC database, and that basically finds images, even if our comet wasn't the target of these images, just images where our comets were taken in, or images where our comets were found in. And then we also use the Minor Planet Center for data collection and the NASA's Jet Propulsion Laboratory to kind of determine the orbital parameters of our comets to be able to track them with the telescopes. And so as we wanted to measure kind of the brightness of our comets, we used a process of quick photometry, which consisted of these three codes: WCS fit, phote calib, and object phote. The WCS fit basically uses star catalogs to make sure our telescope is just taking images in the right part of the sky. And as you can see by these green circles, those represent the star catalogs that we used. And as they match with all the stars in our images, that just means that it's taking pictures in the right area of the sky. And then this phote calib code just uses these stars to kind of calibrate the image and make sure everything is all right. And then the final code, object phote, it uses the Jet Propulsion Laboratory's orbit calculator, and we'll dive into that further a little later in the presentation. But it just uses this calculator to determine like the position of our comet, and then once it determines that position, it just does a process of aperture photometry, which just measures the brightness as it in different images.
All right. So using JPL Horizons, we had our two small body database and our ephemeris system. So the ephemeris system basically calculates the target's orbit in a given time span.
And using this quick photometry, we came upon some problems, and that basically prompted us to describe the importance of checking our images. In this image, or in this picture on the screen, you can see this kind of square on the bottom left is where the telescope was supposed to be taking images of our comet. But in fact, this is where the image was. So it just shows that like you got to check your images to make sure that you don't put in some bad data that's not even relevant for your project. And then furthermore, by checking your images, you can kind of see whether or not the comet is active. As in fact, one of our comets was actually discovered while it wasn't active. So it just looked like an asteroid with a comet-like orbit. And in these images, you can kind of see the comet as it becomes more and more active and kind of gains a little bit of a tail, which I thought was pretty cool for us to be able to observe that process.
So how do we model activity? Using the Google Colab and Python, we had to model the ice types to match the data points or our observed data from the last Congress, CFHT, and the MPC data. And basically, this model calculates how much ice is on the surface that causes the outgassing, which is then translated to a magnitude or its brightness. By modeling this activity, we can predict its brightness in the future. So trial of errors. So here we have a plot of brightness on its orbit, and we have data points from MPC data, and the blue dot, I don't know if you can see, but it represents where we have data. And basically, we tried to model the water ice sublimation, but the model curve didn't match the data we have. And so we switched on over to CO2 model.
Yeah, so as Riza described, when we first tried to make this model, it was actually a different type of ice that we were measuring for. So by switching to a CO2 model, like modeling the CO2 ice, we found that the model actually fit our data a lot more. And even though in some cases, like down in this bottom area, the data wasn't like fully in line with our model, we found, like as we mentioned earlier in like our importance of checking images, we actually found that because the comet wasn't active or wasn't fully active during this time, and then slowly became more and more active, that's why it wasn't really aligned with our model in the beginning. But this chart basically just describes the different data that we used, and then using that data, it just predicts the brightness as it reaches different points in its orbit.
All right, so when is C2019U5 observable next? So here we have a plot, it's the same plot. we are able to observe the comet between 6 p.m. to 1:30 a.m. March 30, 2023. That's also our mentor's birthday. And basically, this plot shows the model of its predicted brightness. And you can see in the red box is when the comet is not observable and heading to solar conjunction, or when it's behind the sun. That's between September 2022 to November 2022. And by having this model, we can predict its magnitude, which we estimated it to be 14.1 meg. As of the comet C 2019 T4, we're still working on that. So Dr. JD, please put the targets in for the last conference check.
And then this plus sign up here is basically where we predicted the like its closest approach to the sun to be and what magnitude it will be at, which she mentioned already. So we want to just say thank you to everyone at the HISTAR program for this amazing week. To our mentor, Erica Bufanda, for helping us along with this project. The Air Force Research Labs for helping to make HISTAR possible. And then Dr. Jan Kleina and Dr. Karen Meach for these photometry and sublimation codes that we use to calibrate our comments. So thank you.
Is there any
All right.
questions?
So if there are any questions. Yes, right over here.
I was up in Lagoon Beach a number of years ago, and I was walking along the beach, and I just happened to look up and I saw this thing go horizontally across the sky. It had a big ball, blue ball with this orange tail. Was that a comet?
Okay, so the question is, I'm going to repeat it up here so that the audience, the remote audience can hear. So the question was, this lady was at Laguna Beach and saw something streak across the sky. It was like a blue ball with an orange tail, is that correct? And whether or not that was a comet, what do you think?
I actually,
Straight across.
I'm going to have to say that I think that was not a comet and a meteorite. Then that's just basically a just like a fragment of either like a comet, asteroid, or any other body in space that is just hitting and burning up on our atmosphere. Usually, when a comet passes, it will be very bright, and oftentimes a lot of comets are not bright enough to see from the Earth. But in occasions, there's a couple big comets that come to pass, and then unless it was on like a certain day that one of those comets was passing, I do not think that it was a comet.
Okay.
Another question? Yes, Michael.
For when you were trying to select your chemical compound, best if you were a good fit for your photometric curves, did you consider a combination of elements, like compounds, like make sure it's in water, for instance?
So the question for the remote audience is, when they considered the compounds for the composition, did they consider having a combination of compounds?
Yes, we did. Actually, we're looking at the Comet C 2019 T4. It might have a combination of both. So yes.
Yeah, just to dive into that a little further, when we tried the different for C 2019 T4, we tried using different models, but we had to alter the parameters to like very unrealistic dimensions. So we actually did not have a model, or we couldn't create a model within our given time for this project to model both CO2 and ice. But that's one of our working theories. We think actually the T4 comet is burning both, or is sublimating both CO2 and H2O ice. And then hopefully we can continue our project and get a good model of that in the future.
All right. One more question, if there's another question. All right, well, let's say thank you to these guys. It's really great to have you. And I'm going to get the next group coming up here, the Dipper Stars group. We'll get the presentation.
Yeah, you introduce them, I can do it.
Oh, okay, great, thank you.
No worries.
Yes, because I'm screwing things up, aren't I?
Yeah.
Okay.
Yeah, you are. Stop pressing buttons.
All right. Come on up, gentlemen. So the next group is, they're looking at what are called Dipper stars. And these are
Stop.
sort of planets
That's
that
meant
are
to be
being
that one.
formed around other stars. Pardon me. And they give us a lot of insight to the planetary formation. So Jet Orion Teagarden is on the left here. Orion, as I call him, is a returning student. You've been working with HISTAR for how many years?
I think 3 or 4 now.
3 or 4 at least, yeah. And he's actually done a bit of work with that, quite a bit of work with asteroids, and his, I think something like a dozen minor planet center circulars. How many do you have? Do you remember?
I think it's around 8.
Around 8. Okay, my mistake. Around 8 minor planet center circulars, but that's, still pretty impressive. James is a new student this year at the HISTAR program, though. He's done a bit of work with asteroids and did quite well at the science fair. And then Brighton is also a first-year student at HISTAR. He actually has submitted a paper to the Journal of Double Star Observations, so quite a good team here. I'll let you go, gentlemen, take over.
Okay, so our project is on Dipper stars, and so Dripper stars. Finding evidence of planet formation around young stars. I'm Orion.
I'm James.
And I'm Brighton. Okay. And so what are Dipper stars? So Dipper stars are stars with recurring, periodic, or semi-regularly occurring dips in light. And so these dips are usually at least 10% less light, and they approximately last for around half a day to 2 days. And so these dips are generally caused by these things called protoplanetary disks. And there's an image of that right here. And it's sometimes, this is more rare, but it sometimes can be caused by exocomets as well. And so what these disks are is it's a formation of gas and dust, which is orbiting the star in the center. And so these disks are how planets and other objects in our solar system are actually formed. And so usually these disks are found around younger stars.
So why are Dipper stars interesting? Well, Dipper stars give us more information about how young stars form planets through their protoplanetary disks accreting. Dipper star light curves are much more unique than light curves of other transients. These dips are both periodic and aperiodic and occur in very short periods of time and are often asymmetrical. So these graphs on the side here, it's going by brightness by time. This one over here is symmetric, which is normally a solid object going in front of the star that blocks the light, which makes the light curve. This one, trailing tail, is normally caused by objects with tail of dust, which makes it dip. And the complex one is normally like a cloud of dust that can or any object that changes shape in front of the star, which has this little jagged dips.
So what have we learned from Dippers, and what more can we learn about them? So we know that Dipper stars are young stars that have remnants of a protoplanetary disk. The dip in the light curves could either be caused by dust in the protoplanetary disk, planet mold, or an exocomet's dust tail. Dippers give us insight on the final stages of planet formation, and as the disk accretes, we're just leaving behind a new planetary system. And the top image showcases a dust disk, And this is basically the stage after the protoplanetary stage. And basically in this stage, dust and gas mostly accrete into planets, and some debris remnants are still remain. And the bottom image is an artist's rendition of an exocomet, and this tail can be indicated of the a light curve in the previous slide.
So our question is, are the stars that we're observing Dipper stars? So our hypothesis is that based on transient alerts and our light curves, we think that we've identified a few Dipper stars that have protoplanetary disks around them. And so we can also use these things called spectral energy distribution graphs, which is this image on the right, to confirm if we find protoplanetary disks. And so what this graph is the x-axis represents the wavelength and the y-axis represents energy of a black body such as a star. And so pretty much what we're looking for in these graphs are infrared excess. And so what that is it's an excess of infrared light. And so the reason we're looking for infrared excess is because the protoplanetary disks emit infrared light more than any other light. And so this graph, this second bump right here, is kind of what we're looking for. That's the infrared excess.
So how do we identify possible Dipper stars? Well, we took note of targets that had high recorded magnitudes, which means they got dimmer than previously recorded for said targets in transient alert databases, such as LCO, which is a ground telescope, and Gaia photometric alerts, which is a space telescope. This change in magnitude presents evidence of a variable star. We looked up potential dippers in Simbad and AAVSO databases to see if they had already been identified.
So how do we characterize our Dipper candidates? So first, we obtain data for our light curve through the assassin photography database. An assassin is basically a ground-based survey which surveys the sky every night. We then use Google Colab to graph our light curves using a programming language called Python. And this is kind of what it looks like. And Matplotlib, NumPy, and AstroPy are all modules that we imported to help us graph our light curves. So next, we obtained the data for our spectral energy distribution graph, also known as SED, from the Virtual Observatory SED Analyzer, also known as BOSA. And BOSA is basically photometric data which they compile and they create SEDs off that. So when we then use the data from BOSA to create our own SEDs and using Google Colab.
So these are the results for one star that I observed called Gaia 16 BBG. And this is my light curve for the star. And so you can see that there's not much clear dips, but there is definitely noticeable dipping in light. And so this is my SED that I made for this star. And you can see this second little bump right here is a little bit of possible infrared excess, which confirms that there's probably at least a little bit of protoplanetary disks and dust around this star.
One of my star targets was Gaia 22 AGO. Gaia 22 AGO had little dips in its light curve like the last one. So that made me gather more data about this star. When I created the SED graph, I saw that there was much more infrared excess than a normal star would. Normally, it wouldn't spike up this high. This can tell us that a large amount of dust is going around the star, and it could be accreting into the star.
Okay, so one of my targets was DTF 1880 FHEF. So its light curve shows very slight dips in magnitude, as seen here. However, it is not a Dipper star, as it doesn't indicate any infrared excess on the SED. SED. This is a sign that the star doesn't have a protoplanetary disk and can just be classified as a typical variable star. This example can be used as a negative control, which indicates what is not a typical star. And in Sinbad, there was one reference of this star between 1850 and 2022.
So conclusions and implications. So what can we do with this information? So our data shows us that, if these stars are even Dipper stars, and it also shows us if there's protoplanetary disks orbiting the star, or possibly if there's exocomets, which is a little more rare. And so what are our future plans for this project? So our future plans could be to learn a lot more about the beginnings of star and planet formations. We also can gather a lot more observations and data of the targets we already have observed and a lot of new targets using the Las Cumbres Observatory Telescope Network. And we can also possibly get spectra of our targets. And with continued observations, we can look for things such as star age, evidence of possible exocomets that are transiting the star, and the composition of the star, and a lot more. So thank you.
All right. So, yeah, do we have any questions? Yes.
Can we see different stars, and if we can we distinguish them with stars just with our eyes?
Okay, so for the remote audience, question is, can we see and distinguish Dipper stars just with the unaided eye?
So probably not, because these dips occur over several hours, and at the shortest of dips, it's usually half a day. So it's not necessarily like it's dipping in light within seconds or whatever. And so probably not is what I would say.
Okay. All right. Yeah.
It was hard to find a linkage between when you're taking a star looking at like the negative this at plus and then going to your like your spectral profiles immediately like the IR. To examine, do you consider wavelengths besides IR? Because it seems difficult to kind of create like an intuitive.
Okay, so the question is basically, did you consider using something other than infrared excess, another wavelength band for diagnostics as a diagnostic tool? Okay, good.
So we did not use any other wavelengths other than infrared, and this is because it shows the most infrared light, much more than other wavelengths. We probably could have to see some, but infrared usually gives us the most results, so we typically just stuck with that.
Yes.
You mentioned that the dips in light seen in different stars could be from either or from like protoplanetary disks, decimals, or like an exocomet. Is there any way to tell what the differences between which of those are different?
Okay, so the question is, the Dipper stars can be exoplanet or protoplanets, comets, or sort of a debris field. How do you distinguish between those cases? Can you tell which is which?
So the light curves that were shown in one of the first slides, kind of the shape of the dip can show us a little bit of that. And then also, if we were to get spectra and more observations, then we could see lithium within our data, which would show evidence of exocomets. And a lot of it comes down to the infrared light, because the most infrared light is from the dust and the gas, and then also the shape of the light curve. So if it was an exocomet, it would be like this middle one, which dips faster and then kind of comes up a little slower. And if it's gas, it's usually some complex graph like this.
Any other questions? All right, let's thank them. And up next, we are going to be hearing about astroseismology. So Julie and Julia, they sound similar, but they're spelled very differently. Julie is a student that I've been working with a little bit in the school. At her school, I've been going over there and kind of doing an astronomy club. And this is her first year at the HISTAR program. And Julia also is a student I've been working with. She was, what did you do at you got to the state level science fair, if I recall? Yeah, so she got an award there, doing some exoplanet research, right? And so this is a little bit different for her, but hopefully been enjoyable. And so they're going to be talking about basically starquakes and astroseismology.
Nice control. Control this in outer space or down. Okay.
Ready. Am I allowed to just present from here? I'm gonna hope so. So hi, I'm Julia and I'm Julie. We did our presentation on starquakes. Just want to quickly mention that this little animation over here was made by Julie, which is fun and cool, and I think that's awesome. There we go. So an important principle that kind of allows all of our research to happen is that sound waves and pressure waves are correlated. And basically, I'm going to use the example of a conch shell. So when you blow into a conch shell, you are creating pressure, and that pressure, when blown through the shell, emits a sound. And with different sizes of shells and how much pressure you blow into them, you get different sounds. So that's similar to kind of how stars work, and we'll get that into that later.
So what's in a star, or what are its kind of layers? There's the chromosphere, photosphere, convection zone, radiation zone, and core. And for our project, we will be focusing mostly on the convection zone. So stars are kind of like giant firing musical instruments.
And that will be answered later, but so the convection zone of a star is, you can kind of think of it in relation to the Earth. It's like the Earth's mantle. So like the layer underneath the crust. And this is where most of the seismic activity occurs, similarly to in the Earth. And this seismic activity is driven by convection currents, which are kind of illustrated here. And basically they bounce around in, oh, thank you. That's cool. Yeah, they kind of bounce around in the mantle, and yeah, those are our pressure waves are wiggling around. And these result in oscillations or wiggling that can be seen on the star's surface. So even though it's happening beneath the surface, it translates to the outside in a sort of oscillation. And there's different types of oscillations, which could be kind of thought of as when you're like hitting a drum, or like hitting the surface of a drum, with like the red on these different diagrams being like an up, and then the blue being a down. And there's different sorts depending on, depends on a lot of factors, but including size and speed and density of the star. Cool. So the official term for studying starquakes is astroseismology.
It's the science of using cellular oscillations for the study of properties of stars. So what kind of telescope that we used to get this kind of data was the Kepler Space Telescope, because it's in space. I know that might not make sense, but it's better for the telescopes to be in space, because in order to do what we're trying to do, we need to take multiple pictures. And if it was on a ground-based telescope, then we couldn't do that, because we can't just hog up the ground-based telescope.
Yeah, and these like taking multiple pictures, this is called short cadence data. And basically we need to take a lot of pictures over a very long period of time to be able to observe these like very, very small oscillations on the stars. So I believe for this specific project, the amount of time was about 30 days. It's 30 days, and you take a picture every minute for 30 days. So that would be pretty much impossible to do with a telescope that was here on Earth, because different astronomers need to use those telescopes for other awesome projects, and we can't take it for a month. And also, like less importantly, but it is useful to know, is that with the Kepler Space Telescope being in space and not on Earth, we eliminate any noise or disturbances that could come from the atmosphere or like the weather or anything funky like that.
So a question that we wanted to answer is, how is radius and frequency related?
And this kind of this is our method that we sort of implemented to answer this question. So this is all being done in Python in Google Colab, which is a more user-friendly educational version of Python, about user-friendly could ever be used to describe Python. And we used in a little, I guess, an app or a module called Light Curve, which allows us to make light curves of stuff.
Yeah, so we imported our data and we plotted the light curves with the light curve app.
And then from that first light curve, we had to remove outliers, normalize it, and stitch our various light curves together.
Then we changed it from flux versus time to power versus frequency.
We did this using a Fourier transformation. And then we basically did this because when it's on an axis of flux versus time, there's all the different frequencies and different wavelengths, or power waves, sound waves, pressure waves, not bad. They're all jumbled together, and we want to be able to see them separated. So that's why we sort of changed the axis, and it's a mathematical formula. And then we looked for an oscillation. So on this little guy over here, this is our oscillation. And this is nice. This is a very lovely little example because we can just look at the light curve and see that. We don't have to do any math or scary things. But most of the time, that doesn't happen. And we have to do math and scary things. So that's what we did. Because here with like most of our stars that we were observing or using for this project, we couldn't see anything. So we had to do more stuff.
Which is very challenging. And whenever you can't see oscillation, most of the time it's caused by bubbling on the star's surface, which kind of cancels it out.
So like all this bubbling, it kind of masks the oscillation or the stuff that we're supposed to be trying to see.
If oscillation is found, we can easily find the frequency of max power just by looking at it. But if it's not, then we have to run an equation, which you can see at the bottom.
Yeah, and we did this equation in Python, so we didn't have to like manually write it out because we're cool that way. And what this is trying to solve, it's a lot of big things, but there's we need things like the mass of the sun and the mass of the star, as well as the radius and the temperature of the star. And then here we had some information for, was this 10 stars? I think it was 10 stars.
Yeah, we split them evenly.
Yeah, we split them evenly. So we each kind of took 5 stars and ran them through our program to try to get our frequency of maximum power, which is our new max. This is just another name for that. So for here, this big number is a KIC ID, or it's like a stellar identifier. And it's just sort of a name. It's like a long name that we can type into the Kepler Space Telescope database to find information on that specific star. And then over here is our stellar temperature, and that's just how hot the star is in Kelvins.
The radius is just the radius of the star, and the new max is the frequency of maximum power.
So this was kind of our, I guess, result. And each of these, each of these plots is one of the stars that we did. And the general trend that is being shown is that as the stellar radius increases, the frequency of maximum power decreases. So as the star gets bigger, the frequency gets lower. And so that kind of answers our question. So our radius is related to frequency because when the radius increases, the frequency decreases.
This is one of the ways that stars are like musical instruments. It's also like, if you don't understand it, another way is to word it is like a smaller instrument is a higher sound. So it's like, you know, if it was like,
You think You can think of like an alto sax versus a tenor sax. Like they're the same instrument, but one of them just has a higher sound than the other one.
And it's basically like that too with stars.
Smaller stars, higher frequencies. Oh yeah, and a quick shout out. I would just like to, I think we would both like to thank our mentor, Buntree, for helping us out so much. Because this was, when we first started this, we were kind of just like, whoa, this is a lot of information. It's really cool, but we don't know what's going on. And Buntree really, really helped us understand this complex and super interesting subject. And then also, thank you to JD and for all the people who are involved in making HISTAR a possibility, because this is like a really amazing opportunity for kids our age. So yeah. Any questions?
Okay, uh-oh, you got one from the mentor. That-
Oh.
Okay, you're gonna, yes. So do you know if the oscillations are correlated to the size of the convective cells of the stars?
Like inside the convection zone or like on the
Inside the convection. Is it just the stellar radius or is it the size of the convection zone specifically where that is correlated? Okay.
The size of the convection zone does matter, as well as things like density, because it just affects it by, it does. Not exactly sure why. I haven't gotten into that, but it does.
Good, good. Other questions? Nothing on the chat. All right,
Alright.
great.
Thanks.
Well, let's give them another round of applause. Fantastic. Good. Thank you. And if you haven't been up here, you know you should be. All right, yes, so, again, we have some famous people up here. In case any of you have not heard, there is actually a press release out on this program today. If you jump onto Maui News Now, we were one of the stories that was on there today. And so our third group, this is back in black, very nice. So this is our HEN, our active galactic nuclei or black hole group. And Holden Suzuki is a returning student for HISTAR. He actually is gunning to be the most attended, the student that has attended the HISTAR the most times. And he's on track for that. He's actually done some work with everything from the SpaceX Tesla to near-Earth object impacting the Earth. Turned out to be a satellite. And also, he's been on several minor planet center circulars. Annika and Shetta, did I get that right? Yep. Okay, yes, you finally have trained me, thank you. She's been the black hole student all along. Has done very well at the state and the local state and state science fair. Has been to the International Science and Engineering Fair this year. And then the third student who is presenting from online, Sydney Moss, he was part of the discovery of the first Trojan comet, which turned out to not really be a Trojan comet, but it was still very exciting. And so I will turn the time over to our Back in Black group, otherwise known as the Men and Women in Black. Does that work? No. Okay.
Well, my name is Holden Suzuki,
I'm Monica Anchetta,
and we're studying NGC 3822.
back
In black.
So
a little bit before we get into it, some background information. So this right here is an AGN, or an active galactic nucleus. Active galactic nuclei are centers of galaxies with notably fluctuating brightness, and this is usually due to a supermassive black hole in the center, in the center of it. So recently, one of these AGNs, NGC 3822, has shown an increase in brightness. And our goal is to measure the mass of the central supermassive black hole through analyzing the H beta line and its brightness over time. So some terms to know. Again, AGN, active galactic nuclei, reverberation mapping. This is a technique that we use to measure the mass. More on that later. And then the spectrum. If you're not familiar with the spectrum, you can think of it as like a graph. On the x-axis, you get wavelength, and on the y-axis, you get brightness or the intensity of each wavelength. So the particular emission line we used, or well, emission lines are basically they're like certain places on the spectrum where for certain gases, for certain elements, they are brighter. This one we use H beta, hydrogen beta, which is emitted by hydrogen at a certain wavelength. And we, it was, I'm sorry, I blinked out. So we also observed the broad line region. So if we go back to the previous slide, that that place right there, the broad line region, that's where we're getting our measurements to. So then we also have flux, which is basically our brightness on the spectrum, and the continuum. So on the spectrum, there's like a bottom noise, and then we have emission and absorption lines that are going up and down. Sorry. Up and down. So that's your continuum. And then finally, we used our measurements of the H beta to make a light curve. Light curve is brightness over time. That's it.
Hello? Can you hear me? Okay, there we go. Sorry for the delay. The data sets we used were collected from UH-88, which is a 2.2 meter telescope on Mauna Kea in the form of spectra. This here is all of the data points that we used collected on multiple different days. Each line is a different day.
Oh, sorry. Oh, it's because of the triangle. Oh, sorry. There you go. Is that right?
Okay, yeah.
There we go.
So reverberation mapping is basically when photons from an accretion disk are struck. So this can cause a light, well, there's a light travel delay also, which is basically how long light takes to get to that accretion disk. So the broad line region is basically how wide that line is. So basically H beta is basically the emission line we're looking at, and the broad line region is basically how much that emission line has been skewed by either blue shifting or red shifting. Our goal is to measure the mass of the black hole by detecting the time delay between the continuum and H beta light curves, because that'll give us a good idea of how large it is and what kind of size it's got. Our procedure, we observed NGC 3822 with UH88 for the days of from 2022-03-11 to 2022-05-23, and we collected spectral data. So spectral data is just basically how bright it is at different wavelengths. We measured the energy of the H beta line for all the spectra after subtracting out the local continuum. So continuum is basically just how bright it is just in neutral, when there's no emission lines, when it's just what the color is, just without emission line, basically. So after that, we found the time delay from the accretion disk around the black hole to the edge of the BLR. And we use that all to calculate the mass of the supermassive black hole. So as you can see, we have an equation up here. This is the orbital velocity. This is the universal gravity. This is the mass of the supermassive black hole. And this is the radius. So basically, we use this to calculate how large the supermassive black hole was.
To get the delay time for H beta, we had to take the measurements and use what's called the trapezoid rule under the H beta line. If you look below, it shows that we cut up the area under the line into, oh, slide change, sorry. We cut the area under the line into trapezoids and get the area of those. If you look at the first graph beneath the text, you're going to see that we're losing quite a bit of data there. The way to combat this is just really to use more trapezoids, and you're going to get a much closer example. Over on the right of the data, you're going to see, I believe it's 311 that we got this data from. This is the H beta line that we measured the area under. We just subtracted all the area under it to get the H beta. The area under it is called the continuum.
These are just some more examples of the data that we got. So it's all redshift corrected, and it just gives you a good idea of the line where the continuum is. So this line here is the line of best fit for the continuum, and it gives us a good idea of like what we're chopping off, basically. So everything above this is just the H beta line. So when we finished, we basically using the data.
Sorry.
So using the data from UH88, we were able to compare the H beta light curve to the light curve of the average continuum between 5,500 angstroms and 5,750 angstroms to see if there were any common features. What we found is that there were. It was just that they were pushed back 2 days, which makes sense because, as we said, there's going to be a time delay on the H beta. So in conclusion, we found that.
So in conclusion, we determined through the analysis of the features of the H beta line that the time delay of the light to reach the edge of the BLR is 2 days. So like Holden said before, for these graphs, if you'll look, between peaks for the H beta and the continuum, there's an average of like a 2-day delay. And so that's what we used for the radius of the BLR to calculate the mass of the supermassive black hole. And so after we ran those equations, we found that the mass of the supermassive black hole in NGC 3822 is approximately 1.56 times 10 to the 6 solar masses. And so with the upcoming data, with more upcoming data, we can refine our measurement of the orbital velocity of gases. So we basically use just an estimation for the orbital velocity, right? So by having more data, we'll be able to find an even more accurate mass for NGC 3822. And we'll be able to use this technique on many more supermassive black holes in the future. So we can learn more about the universe we live in.
We would like to thank our mentor, Anna Payne, for guiding us through this project. We would also like to thank everybody who lectured and mentored at HISTAR. And last but not least, we would love to thank the HISTARS sponsors for making this program possible.
Some of the sources we use for either the images or just information that we were providing.
Okay, any questions?
When you were considering getting to the
So the question is, did you not have access to the functional form of that so that you could do a true integration instead of a numerical estimate? Is that?
Yeah.
Okay.
How do we say that? Yeah, we didn't have a functional form to the observations. They were, we had to use an estimate to find the area of the age beta. They were not like,
So yeah, there's really not a functional form for these because what you're doing is you're measuring brightness each wavelength and trying to integrate under that curve each that's defined by these points. So, yeah. Okay, you said you had a second one.
Now understanding for when we're trying to determine direction, did you apply some average of all of days for the respective wavelengths?
Yeah, so when you're finding the red and the blue shift, how did you combine observations over several days? Was it a straight average or a mean, or did you apply some other approach?
we basically just used an average. It was just like an estimated average of the orbital velocity. We didn't have the time to do an exact measure for the orbital velocity through using redshift and blue shift.
We have any other questions? Okay, I'll put one in here. So you say that you determine the mass from the time delay on from H alpha, right? And then basically, so that's the size of the Schwarzschild radius, or what is that? And you measure, estimate the mass from there, is that correct? Or
We measured the time delay from.
Yeah.
Okay.
Sorry if I'm making you go back and repeat things.
Okay, no worries.
Yeah.
Basically, what we were doing is that with the time period, we kind of it did not want to go back on our slides. And there we go. So if you look at our equation, time is just the time delay between the black hole and the BLR. So basically, that's the time it takes for any kind of light or energy to go from the black hole to the BLR. So it gives you a general idea of just the size of that accretion disk, and that can give you a good idea of the size of the black hole itself.
Okay.
Yeah.
And then the size is directly related to the mass, is that correct?
Yes.
Yeah.
Good. All right. Well, let's give them an extra round of applause. They had a little bit of technical challenge with the most presentation, but did a great job. All right. Well, thank you all for coming, and that's the that was our last group, and we invite you to spend some time talking with us a little bit. I right now need to take all the students in to take care of a couple things, and we'll be out in say about 20 minutes. to join you if you are joining us for